Bismillahirrahmanirrahim, starting with the name of Allah, who is most gracious and merciful. Assalamu alaikum and good morning, everyone. Today is the second lecture of the course Nanoscience and Nanotechnology. In the previous lecture, Dr. Naur gave us introduction of nanomaterials, their significance, their classification based on their structure and their significance in research. Today's lecture is focused on synthesis and properties of nanomaterials. In this session, we will know about the different methods of preparation and we'll learn about properties of nanoscale materials which are important for research and industry. Now, I would like to invite our esteemed teacher, Dr. Naur, to this virtual stage. Please, sir, share your screen and it's all over to you.
Today we are going to talk about the synthesis of nanomaterials and especially talk about the main synthesis methods from the two categories. Yesterday we talked about the nanomaterial and what the natures of nanomaterials and why the people change from micro scale and macro scale and micro scale to nanoscale and why they do this and what is the beneficial for this and what the major types and especially classes based on the material, based on the shape, dimensions, and also the main rules of synthesis of nanomaterials. And also we see some pictures about the different types of nanomaterials. And today we are gonna speak about the synthesis routes. Yesterday also we talked about bottom up and top down procedure. So okay, now you are seeing slide number 3, right?
Yes, sir.
Okay, so we will start with top-down synthesis procedure. So what does the meaning of that? Yesterday I told you top-down, we start from the big bulk materials divided to produce nanostructural materials. And there is a different techniques or different methods. They are usually used or mainly used to synthesize the nanomaterial for top-down approach. This is like mechanical milling. And some of them is chemical, some of them is physical. It's based on some physical phenomena and chemical phenomena, but mainly the bottom-up is chemical, but and also mainly the top-down is physical. So we have a mechanical milling, or we can say ball milling, and we will talk later in details. Electrospinning, lithography, sputtering, arc discharge, and appellation. Okay, laser appellation. So let's go for mechanical milling. Mechanical milling is a cost-effective method producing material at nanoscale level. In this way, you can do any material to nanoscale, any material, even tree leaves. Tree leaves. When you have tree leaves dried and use it and put in the ball miller, then finally you will get it nanoscale. Any material. Oh, sorry. Now you see slide number 4, right?
Exactly, sir.
Okay. So by using mechanical milling, or usually the instrument is called ball milling, you can prepare any material, anything, even the bone, animal bone, you can change nanoscale. Tree leaves or leaves of tree, you can change nanoscale. But it's better to do in proper way because the mechanical milling means usually it is used to destroy the bulk material to nanostructural materials. And in this case, what is the issue? And the people using for alloy, for carbon material, for every inorganic material, like for example, zinc oxide, or titanium dioxide. In macro scale, you can change to titanium dioxide nanoparticles, sodium hydroxide, magnesium hydroxide. All the inorganic hydroxide, metal oxides, you can change to nanoscale using a ball milling machine. I will explain to you what is the mechanism for that. The ball milling machine is simple machine. You can find it everywhere. The machine is like capsule. It could be ceramic capsule, and the capsule containing some balls. That bolts sometimes, if the capsule is steel, then the bolts will be steel. If the capsule is ceramic, then the bolts will be zirconium oxide. And you put your materials, and during the collisions, oh, now slide number 5, you see, right? You
Yes,
see,
sir.
okay.
Yes, sir. Slide number 5.
So I have to confirm every time. Okay, so the ball milling machine, which produce nanostructure material or nanoscale material based on the mechanical milling, is like capsule. And the capsule, sometimes I told you before, can be steel, then the bolts will be steel, ceramic, then the bolts will be zirconium oxide. And you put your material, then after that you start rolling. So some Balmila used all horizontally, some vertically. It depends. And during the rotating, will be mechanochemical energy created. That mechanochemical energy created because the collision between the bolts and the bolts with the wall of the capsule, and between the material, it will create mechanochemical energy. That mechanochemical energy will be sufficient to achieve or to afford the activation energy of the material to break down and destroy to small nanoscale. And in this particular case, you have to put some other soft material, because after breaking the material or destroy the material to become small nanoscale, you have to cover with some other material to separate it or to avoid the reaggregations. Because sometimes, and also in this case, you have, if you are preparing some nanomaterial for the first time using bulk milling, you have to optimize with the time, and you have to optimize with the frequency, uh, and see, because sometimes it will be recombined again, right? So this is the main idea of using bulk milling for the preparation of nanoscale material. There are the many material you can prepare. I told you you can prepare bone, the animal bone. You can change to, because animal bone sometimes is hydroxyapatite and you want to use it for anything. So you can just collect the animal bone and break down, then put in the ball miller. Then you will get nano. It's easier. But it's important for you to know what you're doing and to put some soft material to avoid the aggregation again. Okay. Uh, electrospinning. Electrospinning is one also of the simplest top-down methods for the development of nanostructured material. Electrospinning you can do in your home, actually. You can do in your kitchens. It's not difficult. Yeah, there is a big instrument for electrospinning, but it's very simple, actually. The idea is very simple, because the idea, you need a syringe. First of all, you need to put your material as a polymer solution, for example. For example, some of you want to use he's working in tissue engineering, for example, and he want to prepare some fibers, and containing that fibers have some nanoparticles or something. So he either solves the polymer, like polyvinyl alcohol, for example, and put the silver nanoparticles inside it, and then make a solutions, and then put in the syringe, and there's a volt difference in this, and collector. You need a collectors, you need a syringe, and you need a difference in the voltage. Then you will collect, and based on the nozzle of the syringe, you will change the diameter of the fibers what you have, and after that you make annealing. Then finally you will get nanofiber containing nanoparticles. This method, actually, it's very simple, and you have to there's a many different factors affect on this, like in ball milling, the factor time of ball milling, and the frequency, and the volume. I mean, the amount, because sometimes if the capsule is bigger, then if you put small amount, it would different that bigger amount, and so on. But in this case, the viscosity and the type of the polymers and the nozzle diameter, all of these factors affect on the quality of the nanostructure you produced from electrospinning machine, of electrospinning way. This is Slide number 7, okay, right?
Yes,
7.
sir.
Uh,
Yes, sir. Slide number
this is
7.
this is the schematic diagram representing in the middle about the bulb, the electrospinning process. It's very simple actually. You need even you can collect your material on nanofiber on the. It's mainly for nanofiber actually. Electrospinning is mainly for nanofiber, but nanofiber you can just use different nanofibers, even thermoplastic nanofibers. Other polymer nanofiber. You can use. You can also include some nanoparticles in nanofibers, and after that you make annealing and decalcination, or you can change to others. So it's very simple, not big much, just high voltage power supply you need it. Battery it will be enough. Even battery it will be enough. Yeah, I have construct one machine like this when I was doing my PhD in South Korea. So it's not big issue actually at all. There is a big instrument now, you can buy it if you have a financial aid, but if you don't have financial, you can do it in your in your lab. It's not big issue actually. Uh, the other method is lithography, because lithography is one of the most important top down nanoscale senses, especially for the electronics, because it's useful for developing nano architectures using focused beam. You're using some beam of light of electrons. Then we have two-way masked lithography and maskless lithography, and you just prepare some very very interesting nano dimensions. You can prepare 3D freeform micro nano fabrications, and all the applications is used for the electronic applications. Lithography is very, but this way is expensive actually. You have to have the instrument and you have to have the chamber, and but the other way is electrospinning. That's why I'm always teaching the students and teaching there's a different way to prepare some nanomaterials, and some way need a big instrument or expensive instrument. Definitely it will be directed for some specific applications, but if you are in your lab in Pakistan or somewhere and there's no big financial aid, you can use your brain. Your brain on the top of your neck is free of charge. You can just read and use it, and you will develop many methods. It's not is free of charge. Okay, so you can see here. Yeah, this is slide number 9. Okay, slide number 9.
Yes, sir.
Okay, so this is the way, I mean, focused ion beam. You can see here in the silicon. You are just preparing, and after that you're using QH for wet etching. Then you will find some nanomaterials, nanostructures, 3D. It's very interesting actually, and the people just use it this way for using barbella shapes and for solar cell, because in the application of solar cell you need to have radiance and collect much more radiance. So the people use popular shape and prepare that nanostructure using lithography, because it's but you need to have the instrument. Actually, you cannot do it by yourself in the lab. The other one is spattering, and spattering also you need a chamber, and process producing nanomaterial via bombarding the solid surface. You have a solid surface, any solid surface, and you just need to bombard that solid surface, especially metal, with some plasma or gas or something, and will be patterning some nanomaterials and collecting that nanomaterial. So in this, in using spattering, you prepare aluminium, you prepare all the metal nanoparticles you can prepare using the spattering way. But in this case, you need the chambers, and the chamber should be vacuum, and it's crazy issue. The people using spattering for preparing the electrode in the organic solar cell or hybrid solar cell, using the spattering way, using a special aluminium or something. So yeah, this one of the way to prepare the nanoscale material, by just bombarding the solid surface of the metal using high energy particle like a plasma or gas, then collecting that on the surface. So in this way you can prepare some film of nanoparticles or electrodes or so on. Uh, here you can see this is the way of the synthesis procedure. This is, pure physical way. And here you can just see in the pictures formation of thin film of physical depositions of chromium nanoparticles. The people just use it for different applications, whatever you use. And in this case, we just sputtering the plasma from argon. Yeah, but this way is expensive. If you don't have the chamber in your lab, you cannot do it. But it's better to know, because why you learn about many most. I think you should be focusing much more, because you know the knowledge, and whenever you finish your master, your PhD, and you shift it to other lab, then and you see the chamber, you know why the purpose of this chambers. Sometimes you shift to other lab and you see this chamber and nobody think about it, and this useless. You can use it. It's very simple, right? Arc discharge. Actually, arc discharge is one of the methods using for preparations of carbon nanomaterials top down. I told you yesterday, the carbon nanomaterial or carbon allotropes is there's a carbon nanotubes, there's a graphene, nanodiamond, carbon nanoparticles, carbon nanofiber, and so on. Arc discharge is one of the methods for preparing of a graphene and graphene way using top-down technique. Because in this case, you just use solid state material. You can use carbon material like this method is common for producing carbon materials such as fluorine, carbon nanorods, carbon nanotubes, fluorine, graphene, and so on. The arc discharge is also a dependence like spattering. You just put the graphite, two wood of graphite, in the chambers and filling the chambers with the pure helium, and the carbon would be vaporized using the arc discharge between the two ends of the graphite roots. Then finally you will get, and by tuning the procedure, you can change the shape and dimension of the product. But anyway, you start from top down because you start from graphite roots, okay? And the graphite root will be vaporized. This also, you need a chamber to be in your lab. Without chamber, you cannot do anything, okay? Laser appellation, actually, this is one of the interesting way or interesting methods to prepare nanomaterial. And Professor Mustafa Said, he one of the father. No, he is the only father actually of the metal nanoparticles like nickel, iron, gold, silver, and so on. He's a physical chemist scientist. He just prepares some metal nanoparticles from different way. And finally, he just used the laser appellations by scanning. You have a silver ions, silver salt, or you have silver nitrate, and dissolve in the cuvette or something, and the silver ions. Then make a screening up and down, right and the left of the laser. Then, because you need the energy to electrons, then you will get silver nanoparticles. It's very simple. And that method is you need just laser source, and you don't need to other way, and also you don't need to any stabilizations or capping agent, or you don't need to anything. You don't need to capping. No need for capping agent. No need for reducing agent. Just up and down screening with the laser beam, up and down, right and the left, and you will change based on the frequency, based on the length, wavelength of the lasers. You will get different size of the nanoparticles. Here I will show you some of the nanoparticles produced using laser appellations, and based on the wavelengths, based on the frequency, fluence, and everything, you get different size, and also you get different size distribution. Like I told you yesterday, there is a now other application.
You say your voice is not clear.
Some of you, his professor asked him, we want to work in this way or some different way. Then he's going to prepare some nanoparticles. He should optimize that size. to see what is the optimum size for the best performance for the applications. He should not only use one size. Okay, it's fine, and no, it's not good. It's not good at all. You should at least optimize the size for the application. First of all, if the method of synthesis is the first time for you, then you have any way to optimize the synthesis procedure and see this is the best time after this time. And if you are using this material for this application for the first times, you have also to prepare different size to see what is the optimum size for the optimum performance. It's very, very important actually, especially for the students like doing master or PhD, because it's a thesis. You will not do it once again. You will do it only one time in your life. Nobody will doing two PhD is only doing one PhD, and he's only has in all his life he has only one thesis PhD. So you should be careful for this issue. Let's go for the other side of the synthesis of nanomaterial is bottom-up synthesis procedure. Bottom-up, I told you yesterday, we just prepare the material or build up the nanomaterial from the bottom, from the atom, from ions, molecule, cluster by clusters, and that techniques you need some, some precautions. You have to take it to finally produce some nanomaterials. So the main methods for that, we have a chemical vapor depositions. We have a solvothermal and hydrothermal methods. We have a sol gel methods. We have a soft and hard templating methods. We have reverse Meisel's methods. Okay. Let's go for chemical vapor deposition. Actually, chemical vapor deposition or CVD is one of the famous methods for preparation of carbon-based nanomaterial. It's only for carbon-based nanomaterial. So in this case, you have a chamber, and the chamber is filled with, you use the gas, actually. You make a vaporization of the gas. You just insert the propane or methane, whatever gas you insert inside the chambers, and you make a decomposition of that gas. Then the carbon will deposit it in the catalyst. You just put, anybody of you know about the tube furnace? Tube furnace. Okay. CVD is similar like tube furnace, but a tube furnace is like a cylindrical tube inside the furnace, and you just heating or carbonize the material at high temperature. Same, but you just make decomposition for the gas. In this case, you just insert the methane, for example. If you are going to prepare some graphene, for example, you put some catalyst, some substrate inside in the bottom of the chamber, some substrate and catalyst in the substrate, and you insert the specific flow of the gas and increase the temperature. The gas will be decomposed in this environment and deposited as a carbon atom, and it will find the catalyst, and the catalyst will direct the carbon to arrange in some specific array. Sometimes if you need a carbon nanotubes, it will be cylindrical. If you need a graphene sheets, it will be layer structures going into and there's a many catalysts they are using. Like for graphene, there are some specific catalysts like nickel, cobalt catalyst, because it provides multi-layer graphene, and the copper catalyst provide monolayer of graphene. It depends what to do, but this process actually is very tough because you need to make a tuning too much time. Even I know one of my colleagues, he has a CVD till now, since 10 years. Till now, he could not achieve single layer graphene because they could not produce. They produce multi-layer only. Okay. The other method is hydrothermal or thermothermal, but this method is very common for preparation of metal oxide nanoparticles or nanoparticles like titanium, zinc oxide, also MOF. But why is the difference, and what is the instrument you are using? You're just using some autoclave. Stainless steel autoclave is filled with Teflon, shell inside, and you just put the difference between hydrothermal and thermothermal. Hydrothermal and thermothermal is the same. You just put your material, and like titanium salt or something, inside with water. Is you use the water as a solvent, then it's hydrothermal, because in this case you put your material reactant inside the Teflon vessel and seal, then put it in the stainless steel, then put in the oven and increase to 160, for example, 160 degrees centigrade. Okay, then the solvent will be evaporated, then it will make a vapor pressure, and at high temperature, during the high pressure and the high temperature, will reduce your material to nanoscale. It's very simple. It's very common. I think, yeah, the brand of the autoclave is bar company, but everywhere can do it by your by you can do it in any place in your country. You don't need to order from Germany or China or something, because autoclave is not big problem to prepare. Some if some technician clever and they have some tools, he can do it. If you use the water, then it will be hydrothermal process. If you use the other different solvent, it will be called solvothermal methods. Again, if you use aqueous means water, it will be hydrothermal as a solvent. It will be hydrothermal process. But if you use other different solvent, organic solvent, DMF, and others, it will be solvothermal methods. And also, this method is used for preparation of MOF, metal organic framework. It's very important, actually. Even it based on, and also you have to be careful to leave at least more than 30% of the volume of the Teflon vessels is free to create the vapor pressure inside, not just full. It's wrong. Okay. Soldier method is very simple with chemical techniques. The people everywhere using this to prepare some different metal oxide nanoparticle like titanium dioxide, zinc oxide, and so on. And finally, after that, you make calcination to produce all this kind of carbon material and to get inorganic material. I mean, you can do it in your lab. You don't need anything. You need just stirrer, magnet stirrer, with heating, sometimes not heating, and beacon or magnet. That's all. That's all. This is your reactor. That's all. It's very simple, actually. I think most of you know about it. It's not a big deal, actually, and it's very common. Really, it's very common because you make a polymerization of the material precursors, then you make sol gels and condensations, and after fine you make evaporations, and you make calcinations, then you get some nanoparticle. This is the main methods for the synthesis of titanium and zinc oxide nanoparticles. Yeah, of course, there's a many factors affect in this process, like molar ratio between the water and the precursors, the pH, the aging time, and the hydrolysis rate, and the nature of the precursors also. But with the clever people, if you one of few master student or something, he can also develop this way, this method. It's not big deal, actually. It's not hard to do. The other method is soft and hard template. Actually, this way the people used before, maybe during between 2010 and 20, they use this method to prepare some nanoparticles, because they use soft template surfactant to prepare some nanoparticles, some polymer nanoparticles, or some inorganic nanoparticles. But after that, the people just not using the template because they have to sacrifice with the template. But mainly soft and the hard template method till now they used for the synthesis of nanoporous material, because it's mainly used for nanoporous material. But for the nanoparticles, the people not using this one because they develop many methods. They don't need to use that one, actually, because the science have been developed much in the last 10 years, so nobody uses template to prepare some nanoparticles, soft template. Before they was used soft template, actually, but mainly soft and the hard template method is used for the nanopores materials, even in organic or inorganic. They use the silica, hexagonal silica ordered mesopores material as the template, and they fill it with carbon precursors. Then they remove the silica, then they get nanopores carbon. This is the mainly way the people just use the soft and hard template methods. Yeah, this is just a schematic diagram showing the hard template, soft template, and colloidal template to prepare some different structure. In the up row, you can find it's preparing some nanoporous material using hard template. The other one is just preparing some soft template. It's surfactant to prepare some spherical nanoparticles, and also colloidal template to prepare also nanoparticles. Uh, Recently, nobody uses it. I mean, I don't use actually in my case. Even I was using before to prepare some nanoporous carbon, but recently I have using the carbonization activation directly because you have to sacrifice with the template, and the template is also cost, and you need to reduce the cost of the material. So in this way, and also you are limited with the surface structures of the template. But if you are preparing some other material, then the optimizations and the dream is open for you. Uh, reverse reverse license method. Yeah, this one is also very important, and still many people using and everywhere. This one you just put when you put oil doublet in water, make emulsions, then in this hydrophobic you have a hydrophobic core, and you have a tails. This one, the senses will be only in the oil doublets. And sometimes if you have other organic, for example, or other organic solvent, and you put water, the senses will be in the hydrophilic doublet, so water. So that's why we say reverse Mises method, especially for nanoparticles. Mainly this method used for the preparations of the thermoplastic nanoparticles, like polyethylene nanoparticles, polypropylene nanoparticles, polyethylene oxide nanoparticles, because finally they prepare some hydrophobic nano polymer nanoparticles. But for metal oxide nanoparticle, nobody uses it actually. I mean, it's not familiar. Uh, Based on the, because that's why we are using, you are saying it's nano actors, because the doublets is the actors. And based on what you need, you can change water, oil in water, or water in oil. It depends on what you need. Today we have finished the lectures, and hope you understand what I mentioned. And I just do some simple quiz for you, because if we have a training, then we have to have some questions to see the people audience understand what I just saying yesterday or not. So the first questions: give the classification of nanomaterial based on dimension and give example for each. You understand me or not? Are you hearing me or not?
Yes, sir, we can hear you.
So I need a one volunteer to answer the first questions. I need the
So,
classifications of
okay,
nanomaterial
sir.
based on the dimension, and give example for each one. Okay, one to answer these questions, and the other question, kindly mention one example of zero-dimensional nanomaterial, inorganic nanomaterial based type, and one-dimensional carbon based type. Listen, I need a zero dimension nanomaterial,
Okay.
inorganic type based, and I need one dimension carbon, one dimension material, carbon based type. You understand my point, right?
Yes, sir. Yes, sir. Questions are very clear. So, can anyone answer? Please come forward and answer these questions.
Nobody know? Don't be
Me
shy.
too.
Don't be shy. If you are shy to say,
Sir,
just send in the chat. If you are shy to answer in public, answer in the chat.
sir,
Yes, Akhtar, please.
sir, actually we have classified nanoparticle based on dimensions. They are four, like zero dimension, one dimension, two dimension, and three dimension.
Okay, give example for each one.
Sir, I haven't remembered all of them. Next time I will try to memorize them.
You don't remember? Okay. Yes, one. Yeah,
Sanya
Quantum
Sasyam.
dot, quantum,
yeah, exactly. One answer, zero dimension is quantum dot, exactly. One dimension is
uh,
non-wire, it's correct.
Yeah.
carbon nanotubes.
This is one dimension. Yeah, one of you answers one dimension and zero dimension. Still, we have two dimension. What is the example of two dimension? No, nobody. Okay. Uh, who is his hand? Okay, that's okay. Answer.
Sir,
So,
example of zero-dimensional nanomaterials is graphene, quantum dots are carbon, quantum dots, and one-dimensional carbon are carbon nanotubes,
yeah,
I
but
think.
graphene is two dimension, not one dimension. Okay, graphene is two dimension, not zero dimension.
Okay, sir.
Okay, okay. Let's to the example. Yeah, to the example is nano coating. Yes, correct. Graphene. Yeah. Okay, great. So let's go for the second question. I need zero dimension nanomaterial, but inorganic type. I need zero dimension nanomaterial, but inorganic type. 3D, yeah, yeah, 3D. You can say nanopillar, nanopillar.
Inorganic quantum dots.
What? Again.
Inorganic quantum dots are
Yeah,
also
yes,
example
it's
of zero
correct.
dimension
Yeah, it's
inorganic
correct.
dot.
It's correct. It's correct. So I need one dimension carbon based. One dimension carbon based. It's simple. Carbon nanotube. Carbon nanotube is one dimension and the carbon based. Okay, okay.
Yes, sir.
Understand me? So I will answer carefully the two questions. I need the first question to give the classifications of nanomaterial based on dimension and give example for each one. So we have a four types of nanomaterial based on dimension. We have a zero dimensions, we have a one dimensions, two dimensions, three dimensions. One dimension, I told you, zero dimension, I told you it's nano from each directions. So we have a spherical nanoparticles, example, quantum dot, or polymer nanoparticles, titanium dioxide nanoparticle, any nanoparticles. And one dimension is we have a carbon nanotubes, we have a nanowire, we have a nanofiber, and so on. Two dimension, we have a graphene, nanosheets, 2D MOF, and this is also 2D dimensions. 3D, we have a nanopillar and nanopillars, nanopillars, and nanocoils is also 3D. I asked zero dimension nanomaterial, but inorganic based. We have a titanium dioxide nanoparticle, inorganic quantum dot, zinc oxide quantum dot, you can say. You have iron oxide, we have a nickel oxide nanoparticles. It's also inorganic zero dimensional material. And we have a one dimensional carbon based. One dimension means, first of all, we need a one dimension. Let's think. One dimension, you have nanofiber, nanotube, and so on. Then I mentioned carbon based. Then carbon based, even carbon nanotubes or carbon nanofiber. Okay. Have a good day and hope you understand my lectures well, and hope this quiz refresh the knowledge of last lectures. Next tomorrow we will also have a quiz about these lectures to make also refresh about what we gave. Okay, have a good day and bye bye. Assalamu alaikum.
Walaikum assalam. Thank you so much, sir, for another wonderful lecture.
Yes,
As
sir.
usual, your expertise and engaging teaching styles maintained our interest throughout the lecture. Especially your dedication towards knowledge of science and technology is commendable. As we conclude our day two, I express my gratitude towards each participant. Your enthusiasm and interest make it truly rewarding. Thank you for your contributions today. Take care. Allah
Okay.
Hafiz.
Excuse
Bye
me,
bye.
Natalia.
Excuse me,
Do you have any questions?
Ma'am,
can you
it's
please share the slides so that we can
question
wait on
answer
screen?
session.
Okay, we will share it.
Yeah, thank you so much.
Ma'am, excuse me, ma'am.